Hello, this is Professor Rakesh Singh Settleman from Indian Institute of Technology. Uh, Today, I'm going to talk about one very interesting topic, which is called MIMO wireless. And in the MIMO wireless, I'll focus on inter-antenna interaction. So I can understand in this interdisciplinary online refresher course on science and technology, we have people from science background and engineering background, from all kinds of backgrounds. So if you are from engineering background, then you must be knowing what is MIMO wireless. It's one of the buzzwords in technology in today's world. But if you are from science background, you may not have heard of this MIMO wireless, but I'm sure after listening to this brief talk, you'll be able to understand a little bit about MIMO wireless. I'll try to make it simple as much as possible. So before starting the talk, I want to acknowledge my students who have worked significantly in this area. First is Mr. Mohit Mishra. He's in the final stage of his PhD thesis. Then next is Dr. Sumantri Chaudhary. He actually recently defended his PhD thesis. And next is Dr. Anirban Boyle. He defended his PhD thesis and he's working as a postdoctoral fellow at the INRS EMT Montreal, Canada. Then finally, Dr. Bridges Kambani. He's actually working as an associate professor, assistant professor at IIT Roper. And I also would like to acknowledge my collaborators and this Professor Alphonse from NTU Singapore, and this is Professor Karu Sele from the University of Technology, Sydney, and this is Professor Sonia Isa from INRS Montreal, Canada, and this is Professor Sivan Cole from the IIT Delhi. So these are my four collaborators who have worked together in this area of MIMO wireless research, especially in antenna effect on the MIMO wireless communications. So here is the outline of the talk. So nowadays, people are talking about 4G wireless, then 5G wireless, and even people started talking about 6G wireless. So we are already using 4G smartphones, and 5G is going to be rolled out sometime soon in 2022 in India. And 6G is actually the next generation after 5G. So the research work for 5G is almost over, but most of the people now start the research work in the beyond 5G and 6G wireless communication. So the fundamental question is, what is the key technology behind this 4G, 5G, and 6G generation of wireless communication or mobile communications? The answer is MIMO wireless. So MIMO wireless is the key technology behind 4G, 5G, and beyond 5G or 6G wireless communications. So that is the topic of discussion today, and it's going to be quite interesting. So this MIMO wireless itself actually evolves a lot from the starting. So at the starting, MIMO wireless was proposed as a single user MIMO somewhere in 1992-94. And this is the idea of that MIMO wireless. So in this kind of single user MIMO wireless, you have a transmitter, you have a receiver. Transmitter will transmit the signal, a message, and information. Receiver will receive the message or information transmitted from the transmitter. So this diagram shows that single user MIMO where you have a terminal which is called a transmitter, a terminal which is called a receiver. So this transmitter will send some message and information, and receiver will receive the message and information. So that was a very primitive single user MIMO, which was proposed somewhere in 1992-94, around that time. Somewhere in 2007, this single user MIMO has actually moved to multi-user MIMO. So this diagram will show you that. So everybody knows what is mobile communication. So in the mobile communication, you have a cell tower, which is actually called as base station. And this base station will employ many antennas. Here you can see this Y-shaped structure is the symbol for the antennas. You have 10 of them. So that's the typical number of antennas base station employs, around 10 plus antennas. And this base station will serve mobile users in a cell which is hexagonal in shape. So every base station will serve one many mobile users. So mobile user 1, 2, and mobile user K. So K number of mobile users in a cells. So now we have many users here, user 1, 2, up to user K. So that's why it's multi-user MIMO. So here this MIMO is called multi-user MIMO because we have many users here. In the previous case, we have considered only one user. So it's a single user MIMO, but this one is a multi-user MIMO. So the communication is also a little bit different here. So you can see that base station antennas are placed at the higher elevation and mobile users are at a lower elevation. So whenever this mobile user is sending signal to the base station, we call this as uplink because of this elevation you have for the base station antenna with respect to that of the mobile user antennas. And similarly, whenever this base station antennas is sending signal to the mobile users, this is called downlink. And the extension of this multi-user MIMO was done somewhere in 2010, and it is called massive MIMO. Massive MIMO means this base station antenna we see here is around 10 antennas, but in massive MIMO, the number of antennas at the base station will be massive. It will be in the order of 100 plus antenna. And this technology here, multi-user MIMO, is for the 4G wireless. So 4G wireless use multi-user MIMO, and 5G use massive MIMO. And another technique which has come out somewhere in 2017, this is called cell-free massive MIMO. So as I've told you, every base station will serve users in one cell, which is hexagonal in shape. And in the cell-free massive MIMO, we don't have any cells. So there is some problem with the users at the cell S. Communication is not good. Data rate is not good. Quality of service is not good. So many issues are there. This was inherent in the cellular communication from the beginning. So in the recent proposal in 2017 in the cell-free massive MIMO, they have actually completely removed the idea of cells. There is no longer any cells. So this is called cell-free massive MIMO, and this is projected to be used in 6G wireless communication. So if you look at the single user MIMO, you have a transmitter and receiver, and you can see that transmitter is employing Y-shaped structures are a symbol for antennas. People usually use conventionally. That's a standard symbol for antennas in the wireless communication and antenna community. So here you see that transmitter employs 4 antennas and receiver also employs 4 antennas. It could be any number of antennas. Moreover, in this case also, you see that base station employing more than one antenna, multiple antennas here. Even the mobile user also has provision for more than one antennas, especially in 6G wireless communication. So now what you see is we have multiple antennas at the transmitter and receiver, single user as well as in multi-user MIMO wireless communication. So now in the MIMO wireless, the most important parameter or the heart of the MIMO wireless is the antenna. So antenna is the most important part of the MIMO wireless. So, and you can see that in MIMO wireless, it employs multiple antennas, more than one antennas. So the idea is we want to see what is the effect of antenna on the MIMO wireless. We also want to design more and more efficient antenna, MIMO antenna array for better MIMO wireless communications. So these are some of the topics we'll be discussing in this today's talk. Okay, so the final part of the talk will discuss about a technology which is projected for the next 1 decade. So it has not come. It's a futuristic technology. People from Sweden, there are scientists and engineers from Swedish company Ericsson actually proposed a technology which is projected for 6G wireless communications. And this is called radio stripe networks. Radio stripe networks are proposed somewhere in 2019. They have not disclosed how to implement this, but the idea is this is a technology which is supposed to be used for 6G wireless communication. So here you can see this is a crowded square in a city. There are so many users, thousands of users. So it has become really difficult to provide a bit good quality of service and data rate for so many users. So what they have projected is that we have many buildings in a city square, and we can use the faces of the building, facades of the building. There you can actually roll out these structures here are called radio strike networks. You can roll out on any kind of surface. It could be the facade of the building, or it could be, I mean, at train station or auditorium, anywhere. So we'll have a lot of discussion on this. So these are uh, foldable like a cello tape. It can be rolled out on any surface. So you'll have many of them. Many of them have shown just 3 of them, so that it can give very good quality service and data rate to all the users. And that's one of the aim of the 6G wireless communication, ubiquitous communication anywhere, almost everywhere. So that's the technology for future. We'll spend some time on that at the later part of our talk. Okay, so let's go back to the 1990s. So, and look at about what kind of wireless communication we used to have. So we still remember in those days we used landline phones. We don't have any kind of mobile phones. In 1990s, if you want to make a phone call, you usually go to telephone booths, and or your home has landline connection, then you can make a phone call. Your office has a landline connection, then you can make a phone call. So at other locations, you are not reachable. No, you cannot make any phone calls. So you have to either go to the telephone booths, or you have to be at home or office where landline connection is there. So the communication, there's a lot of gap here. So you are available only at these 3 locations. At any other locations, you are not available. So mobile phones, if I remember correctly, came in India in late 2000s, and the first mobile phone usually have only audio connections. You can make just voice calls over the mobile phones. So these are the old mobile phones. And what you can see in the old mobile phones, you have a protruding structure here, protruding structure. These are actually antennas. So mobile phones employ antennas. These protruding structures in the olden mobile phones are actually antennas. The new mobile phones has printed antennas, so you won't be able to observe it. So these are actually like dipole antennas, which actually come out from the mobile phone. But nowadays we don't have that. We can have printed antennas. Then somewhere in 2010, we have smartphones. So the world of communication has completely changed. You are accessible anywhere, everywhere where there is network coverage. Not only that, you can also use mobile phone for surfing internet, making video calls, playing games, and so on. So it's one device for many applications nowadays. And some people are even projecting that mobile phones are going to be just like your personal computers in the future. So it will have most of the facilities your computer system has on the mobile phones. So ubiquitous communication anywhere and almost everywhere is the aim and objective for 6G wireless communications. So let us consider present day mobile communications. We are using 3G or 4G smartphone. With this kind of smartphones, you can do many things. You can make voice call, you can watch movie, you can listen to songs, and you can do video conferencing. The list goes on. So this is one device for many applications. We used to have this kind of discussion somewhere in 2009, 2010 in my one of the advanced topic in communication system elective course for final year PhD students, MTech students, and PhD students. So we used to discuss that in one of the course advanced topic in communication system. When we discuss about software defined radio, we actually wanted to have some device which can be used for many applications. And today's smartphone is one real example of that. You can do so many things with one device with today's smartphone. Okay, so one major observation of trend when you go from 4th generation to 5th generation and 6th generation, that is your peak data rate, data transfer rate, the amount of data you're transferring over the channel, over the medium is actually increasing. So in the 4G, 4th generation, you have 1 gigabyte, gigabits per second, 1 Gbps. And in the 5G, it is almost 20 times of that. And in the 6G, it will be almost 1,000 times of that. So the major observation or trend improvement we are having from 4G, 5G, and 6G is that the peak data rate is increased, data transfer rate has increased. And the fundamental question is, which technology is the key in and enabler for this increase in the peak data rate. So what is the technology behind this increase in the peak data rate in the generation of several generation of mobile wireless communications? So MIMO is the technology. MIMO wireless is the technology. So every engineers know what is MIMO wireless, because this is the technology behind 4G, 5G, and it is also going to be there in 6G wireless communication. So let us try to understand what is this MIMO wireless. And we have seen that in MIMO wireless, in single user and multi-user case, we have seen many antennas are there. So what is the benefit of employing many antennas, and what is this MIMO wireless? So let us try to understand what is MIMO wireless. So before going to MIMO wireless, let us try to understand a fundamental device which is used in MIMO wireless in many numbers, multiple numbers, which is called antenna. So antenna is actually a device which we use for transmitting and receiving electromagnetic waves. So this is a device which you use for any wireless communication device. So without this antenna, you won't be able to radiate and receive EM waves. And one good thing about antenna is that along with the EM waves which is radiated or received from the antenna, you can send or receive messages and information. Okay, so this is some typical antennas. This is a base station antenna, typical base station antenna. This is a full duplex printed antennas. These are metal printing you have here with along with this slot here in the metal printing. We have designed this for full duplex wireless communication. This is also one of the technology buzzword in the antenna and wireless community nowadays. So one single antenna for simultaneous transmission and reception of signals. So one antenna can be used for simultaneous receiving and transmitting of signals. Usually what you do is many a times you send signal, and at another time you actually receive the signal. But full duplex wireless communication, you can simultaneously transfer as well as receive the signals. This is actually very good if you want to improve the data rate, and it's actually improved the data transfer rate by almost twice. So this is one printed full duplex antenna we have designed and fabricated in our lab. If you are interested, you can look at our recent paper here. And this is another antenna. This is also very new technology. Here you can see this. It looks like sugar cubes. These are actually dielectric tubes. These are antenna. These are radiating, and it's very efficient radiator for very high frequency in millimeter wave region, somewhere in, let's say, 10 plus gigahertz, 20 gigahertz, 30 gigahertz. Dielectric resonators are widely used because it has no metal losses. Efficiency is very high. We have 6 of them here. We have designed this for avoiding collisions in vehicular radar applications. So if you want to avoid collisions, anti-vehicular collision radars, you can employ this kind of antennas. If you are interested, you can explore our recent paper in IEEE antennas and wireless propagation letters. Okay, so the fundamental case is we see antennas everywhere. So antenna is always there, almost everywhere. When you look out, antenna is always there. So why is that so? Because antenna is the minimum bare necessity for any wireless communication, and we have wireless communication devices anywhere, almost everywhere. Inside our rooms, inside in our office, inside our cars. I mean, we have wireless communication devices everywhere. So antenna is everywhere, and antenna is the minimum bare necessity for any wireless communication device to transmit and receive waves. Okay, so let us check some typical examples. I have observed Wi-Fi evolution for the years, over the years. These are some of the Wi-Fi modems we have used. So this is the old Wi-Fi modems. What do you see here is this is protruded structure. Here is a antenna. And what you can see is we have just single one antenna here. But let's say in recent Wi-Fi modems, we can see two antennas. Two antennas are there. You can see 1, 2 antennas. These protruded structures are antennas. So what you're seeing is that over the years, we're seeing many antennas. Instead of just single antenna, we have multiple antennas. So what may be the possible reason for employing these multiple antennas? So let's see. Let's consider one single antenna transmitting information. This is a symbol, Y-shaped structure is symbol for antenna. This is transmitting information in all directions. Let's say you consider another case where you have two antennas and simultaneously transferring information. Logically, so one good thing about wireless communications, everything is logical. So logically, if you transmit with two antennas simultaneously, then you will be actually transferring at twice the data rate of that of the single antenna. So this kind of idea was the origin of MIMO wireless. And this MIMO wireless actually is invented by one Indian American, Professor Paul Ras from Stanford University. Is the originator of this multiple antenna communication or MIMO wireless. He proposed this somewhere in 1992. And this is the technology behind this high-speed Wi-Fi, 4G, 5G, and beyond 5G or 6G mobile networks. Okay, so let us formally define what is MIMO wireless. Just before that, let us define what is traditional wireless. This is also called as single input, single output system. So here, the name itself suggests that we'll have single input and output will be single. Okay, so this is a traditional wireless communication setup where you have a transmitter which is transmitted signals and information. There you have a receiver. There you have a receiver which will receive the signals and the information which has been transmitted from the transmitter. And you know that all wireless communication device actually employ antenna. This Y-shaped symbol is for the antenna. We have one of them here at the transmitter and one of them here at the receiver. So signals are coming out from this transmitting antenna and signal is received by this receiving antenna. So now what do we have in between the transmitter and receiver is called a channel. That's a medium through which your signal and all your information loaded signals will pass through. It could be free space. In wireless communication, we have free space, or open free space is the medium for wireless communication. So now look at this channel. How many input it will have? It will have input from only one transmitting antenna of the transmitter. It will have output to only one receiving antenna of the receiver. So that's why single input, single output system. So we call traditional wireless communication as single input, single output system. Okay, so let's discuss about the MIMO wireless. What is different from the traditional wireless communication? As by now, I think you must be able to guess that MIMO wireless will actually employ multiple antennas, because we have seen that in 4G, 5G, 6G, we have multiple antennas. Antennas are everywhere, and we don't see only one antenna. We have multiple of them. So in MIMO wireless, transmitter will employ one, two, up to NT antennas, multiple number of antennas, NT number of antennas. NT could be anything. And receiver is employing multiple antenna also, one, two, up to NR antennas. So now this channel here, the medium through which signal is propagating, will have input from NT antennas of the transmitter, and it will output signal to NR antennas of the receiver. So how many inputs we have? We have NT inputs, we have NR output. So multiple input, multiple output system. That's the full form for the MIMO wireless communication system. We have multiple input, multiple output system. So that's the short form of the MIMO. Short form is MIMO, abbreviation is MIMO, multiple input, multiple output system. So that's a formal definition for MIMO wireless system. Okay, so what do we want in any wireless communications? These are many wireless examples you have here. You can have mobile communication. You can have wireless communication using on a car. When you're traveling on a car, also you can have wireless communications. When are you using computer system, you can have wireless mobile communication. Even mobile phones also, PDAs, all this. So any wireless communication system, what do you want? So this is user point of view. We want a higher data transfer rate, higher speed. That's what people usually, layman people use. We want a higher speed in data transmission. And moreover, when we download movie or video, it was downloaded very fast. We have a very high data speed, but then when we download it, there's a lot of error. You cannot watch a movie, you cannot watch a video. You download a audio files, it was downloaded very fast, but you cannot listen anything because there's a lot of errors. So there are two things here. First is higher data transfer rate. Second is less error in data transmission. So these are the two things any users want in wireless communication: higher data transfer rate less error in data transmission. So how do we characterize performance of any wireless communication system? So along the line where user want to have higher data transfer rate and less error in data transmission, we have three parameters people usually look in any wireless communication system. The first parameter is called channel capacity, which is the maximum data rate you can transfer over the channel with minimum probability of error. So as long as you are transmitting up to the channel capacity, receiver will be able to decode the message properly at the receiver side. As long as you are transmitting at a data rate which is greater than the channel capacity denoted by C. R is the data rate, C is the channel capacity. So if you are transmitting at a data rate which is greater than channel capacity, you are in outage. So receiver won't be able to decode the message which has been transferred from the transmitter. There will be a lot of errors. You won't be able to understand anything at the receiver side. So this is called outage. You must have faced this situation in mobile communication also. Sometimes you cannot actually listen to what other people is saying. So in those kind of situations, we have outage. So the probability of such kind of outage is called outage probability. And the first thing is the channel capacity. That's a maximum data rate you can transfer of the channel with minimum probability of error. What is the probability of error? This is the error in the data transmission. And these are the two main criteria. One is the channel capacity, which will give you the maximum data transfer rate you can do over the channel. Another is the probability of error in data transmission. So these are the two main parameters which are along the line what user want. User want a higher data transfer rate, less error in data transmission. So these two parameters, channel capacity and probability of error, is the two most important parameter for any wireless communication device. Outage probability is also very good parameter. We use it, but in this talk, I will not discuss about the outage probability. Okay, so we have understood what is MIMO wireless. MIMO wireless means multiple input, multiple output, where transmitter is employing NT number of antennas, receiver is employing NR number of antennas. So let us try to take simple example for 3x3 MIMO system where transmitter is employing 3 antennas, receiver is also employing 3 antennas. We call this as 3x3 MIMO system. 3 input, 3 output. So 3x3 MIMO system. And let us try to see if I want to transmit 001 over this 3x3 MIMO system, well, how can I do this? I can have parallel transmission. I transmit 1 from the first antenna and 0 from second antenna, 0 from third antenna. I can have parallel transmission. So over a time interval, I can transmit all these 3 bits at a time. But if you consider the seesaw system, that is a traditional wireless communication system which employ one antenna at transmitter and one antenna at the receiver. If you want to transmit 001, you first transmit 1, then you transmit 0, then you transmit 0. So what you are doing is you are transferring 001 over 3 time intervals. So what is the improvement in the data transfer rate when we employ 3x3 MIMO system? Obviously, anybody can guess it. It is 3 times that of the seesaw system. So with respect to the traditional wireless communication system, MIMO wireless will have higher data transfer rate because of simultaneous transmission from all the antennas at the transmitter and receiver will receive all the signals. So this is parallel transmission gives you what is called rate gain. People call this also as multiplexing gain. We'll call it rate gain because we see that there is a gain in the rate of the transfer by employing MIMO system. So a little bit about the mathematics. You don't need to worry about it. I will try to make it simpler and simpler as possible. So now here you see that there are 3 antennas here. So you'll have any number of antennas at a transmitter. So the power which is available to the transmitter will be, let's say, P total power. But then all the power should not go to one antenna. It should go to all these antennas. So how much this antenna has a power provided to this antenna, power provided to this antenna, power provided to this antenna. This is called power allocation. How much power each antenna will have. We have something called very simple power allocation where every antenna is getting the same power. So that is equal power allocation. So if you have total number of transmitting antennas NT, you just divide that with the total power. Every antenna will get PA. equal power. For that equal power allocation, the capacity for the MIMO system, capacity was the maximum data transfer rate you can do over the channel or the medium of transfer, is M times that of the CSO system. M times that of the CSO system. CSO is the traditional wireless communication where it has only one antenna. So what you observe is that for this equal power allocation for the MIMO channel, best MIMO channel, where you don't have any kind of antenna correlation, you don't need to worry about that. So capacity for the MIMO system is M times that of the CSO system. Okay, let us briefly discuss what is this formula you have here. This is called bandwidth. This is called log 2 of 1 plus SNR. SNR means signal power divided by noise power. Signal power is the desired signal power. Noise power is the unwanted power. So higher is the signal to noise ratio, the ratio of the signal power and noise power. We can have higher and higher data transfer rate. So this is the capacity maximum data rate you can transfer of the channel for the CSO system, traditional wireless communication system employing only one antenna. So if you want to improve the capacity for the traditional wireless communication, you increase the bandwidth. That's why people are crazy about the bandwidth. No, you keep on increasing the bandwidth, capacity is going to increase, data transfer rate is going to increase. And another thing is that you increase the signal power, desired signal power with respect to the noise power, you can also increase the capacity of the traditional wireless communication system. And that's for the traditional wireless communication system. But for the MIMO system, you don't need to increase the signal power because you cannot keep on increasing the signal power. There are many issues. If the signal power is very high, you will have radiation effect, biological effects on human beings, animals, and so on. So you cannot keep on increase the signal power. And again, when you increase the signal power, there will be a lot of interference. Bandwidth also is very precious. You cannot keep on increasing the bandwidth. Bandwidth will be allotted by the FCC. You cannot have any bandwidth on your own. You have to buy it from FCC. There will be auction system where they will allocate the bandwidth for different applications. So bandwidth is almost fixed. You cannot change it. You have only liberty of increasing the signal power, but there are so many issues. One is when you increase the signal power, there will be a lot of interference. That is one of the inherent problem in wireless communication. Interference is a biggest issue. So this is not a good idea. Increasing the SNR or increasing the bandwidth is not possible. And increasing SNR is not a good idea. It has another issues, very important issues like interference, then even the biological effects also. But for the MIMO system, you may be surprised. You don't increase the SNR, you don't increase the bandwidth. This is always fixed. You don't increase the SNR, signal power, you don't increase the bandwidth, but then you have capacity, which is M times that of the CSO system. What is this M here? M is the minimum of either the NT or NR. NT is the number of transmitting antenna and the number of receiving antennas. Minimum of that. We'll take some case study in the next slide and understand what is M. So capacity increase with M without increasing power and bandwidth. So it's a win-win situation. So if you have something called large scale MIMO where you have M is equal to order of 100 or 1000, capacity will be 100 or 1000 depth with that of the CSO system. That's why people are using MIMO for the 4G, 5G, and even for 6G wireless communications. You increase the number of antennas, your capacity is going to increase linearly. So let's take simple example to find out what is M, which is minimum NT or NR. So let us look at this example here. You have 7 transmitting antennas, you have 5 receiving antennas, but how many parallel data transmission you can have? You can have only 5 parallel data transmission. You cannot use this remaining antennas. That's the minimum NT and NR. Minimum NT and NR is 5. That many parallel transmission we can have. Because of that, capacity or the data transfer rate will be increased M times. Similarly, if you have 4 antennas as a transmitter and 7 antennas as a receiver, you can only have 4 parallel data transmission. So M is 4 here. So that was the M you have in the formula. Okay, that was the rate gain, improvement in the data transfer rate. Another gain is called diversity gain. What is this diversity gain? Let us try to understand by using this simple 3x3 MIMO system, 3 antennas at a transmitter, 3 antennas at a receiver. So here we actually consider another situation where I want to transmit only 0 bits. So now when I transmit 0 bits from this antenna 1, 2, and 3, it can follow many paths. This antenna 1 send out signals, it will go in all directions. So it will pick up by this antenna 1, 2, 3 of the receiver. Similarly, this 0 bit will be picked up by antenna 1 to 3 of the receiver. 0 bit will be picked up by antenna 1 to 3 of the receiver. So what is the advantage of transmitting same bits from all these antennas here? The idea is if any of the link is down, there's a blockage here, shadowing here, then this antenna won't be able to receive the signal which is transmitted from this antenna 1 and antenna 3. Okay, so no issues. We still have the remaining parts where this signal will reach the receiver. So signal or the message which has been transmitted from the transmitter can be easily decoded from the remaining parts. This is the idea. So, but let's say if you consider traditional wireless communication where only one single antenna is used at the transmitter and single antenna is used at the receiver, if this part is broken, you send 0 bits from here, receiver won't be able to decode the message. So that means there'll be a lot of error at the receiver. So this diversity gain is the number of independent paths you have for the signal to reach at the destination. So here, if you have a 3x3 MIMO system, you can have 9 different paths. 1 by 1 MIMO system, you just have only one path here. This is called diversity gain. So because of this, you'll minimize the probability of error at the receiver side. That means you'll have less error in data transmission. Okay, so let us try to understand some fundamentals on the wireless communication, some parameters we use. One is called bit error rate. So what is this bit error rate? I will take one simple example. Those who have background in communication and wireless communication, they already know what is bit error rate. This is one of the very basic parameter people use in wireless communication performance analysis. Anyway, those who doesn't have background, no need to worry about it. Let's say I'm sending 5 bits from the transmitter. At the receiver, when I detect it, I detect the bits we're sending are all zeros, but at the receiver, I detect 11000. So that means I'm sending 0000, but I'm detecting 1100. How many bits are in error? You have 2 bits are in error. So how do you find this bit error rate? Bit error rate is also called probability of error. So we have 2 parameters in wireless communication. One is channel capacity, which will give you the maximum data rate you can transfer of the channel. And another is a probability of error. This can be calculated as bit error rate. So when I send 5 bits, 2 bits are in error. The probability of error is 2 by 5. This is calculated as number of bits in error divided by total number of bits sent. So it's 0.4. So that's how you calculate the probability of error or bit error rate. SNR, as I've told you, is the ratio of the signal power divided by the noise power. Signal power is the desired signal power, noise power is unwanted. So if you have larger and larger value of this noise power, or let's say smaller and smaller value of the signal power, then your data transfer rate or your probability of error is going to increase. Data transfer rate is not going to be affected much, but the probability of error will be affected much. So higher the value of SNR, signal to noise power ratio, will have better performance in the wireless communication, less error in data transmission. Okay, so this is a typical graph of the probability of error versus SNR curve. What you can see here is that this curve here is for the seesaw system. When you employ MIMO system, slope of the curve will increase. What is the advantage of that? We'll see in the next slide. Okay, so if you consider the simplest wireless channel model, which is called Rayleigh-Fleming channel model, where your transmitter and receiver doesn't have any line of sight communication, all signals will come at the reflection, refraction, or any kind of disturbance from that medium. No need to worry about it. This is the simplest wireless channel model. The probability of error for the simplest wireless channel model for the single input, single output system is 1 by SNR. So 1 by SNR curve will be almost like straight line with this negative slope of 1. But if you consider the MIMO system, multiple input, multiple output system, the probability of error curve, probability of error will be 1 by SNR to the power diversity gain. So this is the power, it will give us the slope here. So slope will be increased. This is always greater than or equal to 1. If you have higher and higher value of diversity gain, this slope is going to keep on increasing. So what is the advantage of that? This is the probability of error versus SNR curve here. So let us look at one fixed SNR, power is fixed. How much is the probability error for the seesaw system? This is the seesaw curve. So it's cutting at this point. You see that the probability error is typically 0.5 into 10 to the power minus 2. But if you consider this MIMO system curve, it is cutting at this point here. So how much is that probability error? Probability error is 0.5 into 10 to the power minus 5. So typically when you employ a very good MIMO system, probability error will be reduced 1,000 times. So the error is minimized 1,000 times. So that's the advantage of MIMO system. Increase of the diversity gain because of the increase in diversity gain. Another case is you fix the probability error in the data transmission rate around 10 to the power minus 4. How much is the signal to noise power ratio SNR? You need around 27 dB. For the MIMO system, you need 17 dB. You have almost reduction of 10 times power required for the MIMO system with respect to that of the system, CISO system. So it's an energy efficient communication. So there's something called green communication. In the green communication, MIMO is also projected to be used because this is very energy efficient. The amount of power we require for MIMO communication with same bit error rate is actually much lesser than that of the CISO system. Okay, there's always two sides of the coin. See, whenever you have something good, you also have some problem. So we want higher diversity gain and rate gain, but what we observe is that you cannot simultaneously increase the rate gain as well as diversity gain. So both of them are actually having a trade-off, which is actually reported by this L. Zheng from MIT. This is a very famous paper on diversity multiplexing trade-off, diversity rate trade-off in MIMO system. So it was published somewhere in 2004. And one good observation is that this paper has 5,228 citations. So many of the people, many researchers actually are targeting, citations of thousands or, 2,000, but then this one single paper is having 5,228 citations. So you can understand the impact of this kind of paper, one paper with 5,228 citations. So in this paper, they have actually simply given the formula for trade-off between diversity and the rate gain. R is the rate gain, D is the diversity gain. So diversity gain is equal to NR minus R, NT minus R. NR is the number of transmitting antenna, NT is the number of receiving antenna. So if you increase this R here, D is going to decrease. If you decrease this R here, D is going to increase. So let us try to do some simple case study and understand this diversity multiplexing trade-off. So now this is a 5 by 5 MIMO system where 5 antennas are employed at the transmitter and 5 antennas are employed at the receiver. So you have a trade-off between diversity and rate gain. So we cannot use all the antennas for the diversity gain or rate gain. We have to actually do some kind of design where some of the antennas can be used for rate gain and some of the antennas for the diversity gain. If I use 3 antennas for the rate gain, I will have 3 times the speed with respect to that of the traditional wireless communication system, which employ 1 antenna at the transmitter and receiver. Remaining 2 antennas I can use for the diversity gain. I will have a diversity gain of 4 because there are 4 different parts here. Okay, so if you want to explore more about MIMO wireless, I have a book on the fundamentals of MIMO wireless communication published by Cambridge University Press, UK. We also have another book, MIMO wireless communication over generalized fading channel with Dr. Bridges Kamani. He was my former PhD student working as assistant professor at IIT Ropur. This is published by CRC Press, USA. Okay, so let us try to understand one thing. We have discussed about, at the start of the topic, I have mentioned about the inter-antenna interaction between different antennas. Okay, so we have NT antennas at the transmitter, NR antennas at the receiver. I have used different colors for the signals which has been transmitted from the antenna 1, antenna 2, and antenna NT. So this is violet, this is black here, this is red here. So we are transmitting different symbols or bits from antenna 1, 2, and 3. But then what you can observe here is that symbols or signals which has been transmitted from antenna 1 to an NT are actually received by antenna 1. It has been received by antenna 2 also, antenna NR also. All the symbols which has been transmitted by the transmitting antennas are received by antenna 1 also, antenna 2 also, antenna NR also. So here at the receiver, all the antennas are receiving mixture of symbols or bits which has been transmitted from the transmitter. So it is very difficult to decode this. Receiver has to do a lot of comparison to find out which symbol has been transmitted from antenna 1 to an antenna NT. So this is a headache for the receiver, and in wireless communication, receiver is much more complex than the transmitter. So what you observe is antenna 1 is receiving all the signals from antenna 1 to up to antenna NT, all the transmitting antennas. Antenna 2 is also receiving all the symbols or bits from all the transmitting antennas, similarly antenna NR. So this is a mixture of symbols you are receiving from the transmitter. So that is the headache for the receiver to decode all the symbols and bits which has been transmitted from the transmitter. So this is also called as inter-antenna interference in wireless communication. Because of employing multiple antennas at the transmitter, you have mixture of symbols received at the receiver, and receiver has to decode each symbol one by one. So it's a lot of processing for the receiver. If you consider your mobile phone has very low processing capacity. So such kind of processing is very difficult with the mobile phone. So what is the cure for that? Is there any way to avoid this kind of situation? There's a technique called spatial modulation, and we have been working in this area for many years, more than 1 decade now, and we have made many original proposals in this area of MIMO wireless communication. So what is the idea? Idea is, what if we just activate only one antenna with using an RF switch here? So you have a special modulator which is connected with the RF switch. At one particular instant of time, you just allow one antenna to transmit symbols or bits. So let's say antenna 2 is transmitting symbols or bits. Then all the antenna as the receiver will receive only one symbol or one bit. So decoding is very easy. You just need to denoise whatever received symbol, you can get the message bits. So that's the idea. Just activate only one of the antenna. Then you don't have any kind of this mixture of symbols at the receiver. Only one symbol is transmitted. So every antenna at the receiver will receive only one symbol. So there is no inter-antenna interaction or interference. So the basic idea for the MIMO wireless was parallel data transmission. So where you can increase the data transfer rate. But when you use only one antenna at the transmitter, the data rate is going to decrease. So how do you increase the data rate for this kind of spatial modulation system where only one antenna is active? That is because we are doing modulation over space. That's why spatial modulation. So we actually number this antenna at the transmitter as some value. For example, if you have 8 antennas, you can do numbering like this 0000001, and last one will be 111. You can do numbering of this antenna in bits. So now what receiver does is that receiver actually, see, antenna 2 was active because you have used RF switch and connected with antenna 2. What receiver does is receiver actually estimate which antenna was used from the transmitter to transmit the signal. That's very easy. So only this antenna is active, then you get high signal from this antenna. All other remaining antennas will get only noise. So that is very low power here. So you can actually estimate which antenna was used for transmitting the symbol from the transmitter. That's the duty of the receiver. Once it estimates the antenna which has been used from the transmitter for transmitting signal, it actually decodes 3 bits, 001. So now without transmitting 3 bits, it's actually decoding 3 bits. So the data transfer rate is going to increase. Let's say we are transmitting only 1 bit from the transmitter, we'll be able to decode only 1 bit at the receiver. So the data transfer rate is 1 bit per second. But if you use spatial modulation, even if we are transmitting 1 bit, because of this antenna indexing you have done here and antenna index estimation at the receiver, will be actually receiving 4 bits. So there is a huge improvement in the data transfer rate. So that's the idea of spatial modulation. Modulation over space by giving antenna index to the transmitting antennas when you have multiple number of antennas, you can have more and more number of bits to index the antenna, and the receiver will do the antenna index estimation, and it will have significant improvement in the spectral efficiency or data transfer rate. So if you are interested in spatial modulation and its advanced version, we have one recent book published in 2021 with my former PhD student, Dr. Anival Bowell, who is a postdoctoral fellow at INRS AMT, Montreal, Canada. This is published by Springer, Singapore. Okay, so that's all about the introduction to MIMO wireless. Let us come back to the inter-antenna interaction. You need to know a little bit about the antenna. So how is the antenna radiating signals? How is the behavior with respect to, theta and phi over the space or over the, see, for example, this is one typical antenna. This is called horn antenna. These are made up of metals, and signal will be radiated from this aperture of this antenna. So this is the typical radiation pattern of this antenna. Radiation pattern will show the behavior of the field radiated from the antenna over space. So now you can see when I have a radiation pattern like this, we have maximum radiation here. So I want you to understand what is antenna radiation from the radiation pattern. So we measure the radiation pattern of this antenna. It turns out to be something like this. And what you observe is that you have maximum radiation here. Maximum radiation along this z direction, and we have lesser radiation along this direction. We don't have any radiation along this direction. So this plot or graph will give you an idea of the field which is radiated from the antenna. Once you have this, you know that there is maximum field radiation, power radiation along this direction, less here, no radiation here. Similarly, this is a wire dipole antenna, which you usually see wire dipole antenna. And wire dipole antenna will have maximum radiation along this direction. It will have lesser radiation along this direction, no radiation along the z direction. So the radiation pattern gives you an idea of the radiation field radiated, power radiated from the antenna. This is called the main lobe of the antenna. This lobe with the highest radiation is called the main lobe of the antenna. These are called side lobes with less radiation. And this is called the back lobe, which is radiated along the back side of the antenna. Signal which is radiated in the back side of the antenna is called back lobe, and which is radiated inside of the antenna is side lobe. Main radiation, main beam. You need all these fundamentals for the next discussion. We are going to do it. So now you have a standalone antenna, antenna 1 somewhere in free space, in open space. So this antenna is radiating like this. This is the radiation pattern of the antenna. So now this antenna will not have any kind of interaction. It's a standalone antenna. But let's say you have another antenna in a little bit far of distance. This is also radiating like this. So fields are going in this direction, this direction. Here also fields are going in this direction, this direction. There is no interference of this field which has been radiated from antenna 1 to antenna 2. That is because these antennas are very far away. So the first parameter for inter-antenna interaction is the distance between the antenna elements. Second is the orientation. Let us look at it. There's another antenna, antenna 3, in between antenna 1 and antenna 2. And this antenna has radiation pattern like this. So fields are radiated along this direction. So now fields radiated from this antenna 3 would be actually picked up by this antenna. So this is inter-antenna interaction. So orientation of the antenna will actually decide for this antenna interaction. So this field and this field radiated by this antenna. So antenna can receive and transmit signal. So it's a reciprocal device. So this field which has been transmitted from this antenna would be received by this antenna 1 here. So there's a lot of interaction because of the orientation of the antenna. But this antenna 3 and antenna 2 will not have any radiation because we don't have any back lobe radiation here. But if this antenna 3 is also having some back lobe, then some of the signal will actually reach this antenna 2 and there will be a lot of interaction. So this kind of inter-antenna interaction is unwanted situation in MIMO wireless communication. So if you have a lot of inter-antenna interaction, the rate gain we have projected at the beginning, diversity gain we have projected at the beginning is going to reduce. We want completely independent channel for every antenna. There should not be any kind of interaction. Okay. So let us try to see case of 3x3 MIMO system for the rate gain. And if you have radiation pattern like this and antenna 1, 2, and 3 are sufficiently far apart all the channels are going to be independent. So you can simultaneously transfer 1, 0, 0 without any kind of inter-antenna interaction. You'll have a red gain of 3. But let's say same situation, 3 by 3 MIMO system, we are still transferring 0, 0, 1 from the antenna 1, 2, and 3. But let's say this antenna has side lobe. This is the main beam of the antenna. If antenna has side lobe like this, signal you have transmitted from antenna 1 will reach to antenna 2, antenna 3, and so on. There will be a lot of inter-antenna interaction. Because of that, red gain will reduce. Similarly, for another situation where you have no side lobe, but antennas are very closely spaced, inter-element distance is very low, then there will be a lot of interaction between this antenna. So the red gain is going to decrease. So this inter-antenna interaction is an unwanted situation. We want to avoid that. Even for diversity gain also, all the paths will no longer be independent. Your diversity gain is also going to affect. The diversity gain is affected, rate in data transmission is going to increase, which is an unwanted situation. So the onus lies to the antenna engineers to minimize this inter-antenna interaction. So antenna engineers design antennas such that this inter-antenna interaction should be minimized. So the parameter antenna engineers use for understanding this inter-antenna interaction is called mutual coupling. Let's say there is one antenna here. This is a symbol for antenna. Antenna 1, it is transmitting signal in all directions. So signal cannot be confined in one direction. So when you transmit signal in the free space, signal can go out in any directions. You cannot just tell signal to go in one specific direction. It will go out in all directions. Okay. So some of the signals which has been transmitted from antenna 1 will reach antenna 2. So this is something called mutual coupling, which is an unwanted situation. Some of the signals which has been transmitted from antenna 1 will actually go to antenna 2, and it will go to antenna 2, and it will create a lot of inter-antenna interaction, which will minimize the rate gain as well as diversity gain for the MIMO system. And the standard here is that if you have a mutual coupling of less than minus 15 dB, it's acceptable. Your MIMO antenna is working fine. If your mutual coupling is less than minus 15 dB, we'll define how to measure this mutual coupling in the next slide. Just before that, let us try to understand what is an antenna. Antenna is a passive device. So until unless you supply some power, some signal to the antenna, it will not radiate. So you have to supply something to the antenna using the source. So the point at which you supply this, connect the supply or source to the antenna is the port. This port here is a point where you connect the signal to the antenna. Then this rectangular shaped structure is the radiator. It will radiate the signal. Until unless you connect anything to this source here, this antenna will not radiate anything. So it's a passive device. So this port is the point where you connect the antenna to the outside wall. So port is a point where you connect the device to the outside wall. Let's say you want to fit some signal to this antenna, you connect to this port. Then this patch radiator, which is rectangular in shape, these are all metal printing, will start radiating signals. This is called microstrip antenna. This is one of the very popular antennas nowadays. It is used for many applications. One point to observe is that antenna, how many ports are there? Only one port is there. And how many radiator are there? Radiator, one element. So this kind of antenna, which is a traditional antenna, is one port, one radiator, one element device. MIMO antenna, let's consider MIMO antenna. These are some typical MIMO antennas. If you look at the MIMO antennas, you will have multiple ports, multiple radiators. You have two radiators here, two ports here. Similarly, you have two radiators, two ports here. So it's a two element, two port MIMO antenna. So the concepts you have for the antenna, which has only one port, one radiator, or one element, has actually has to be changed. It needs to be changed because in MIMO you have multiple port, multiple antenna. So it's a multi-port, multi-antenna elements. So in multi-port, multiple antenna elements, you need to worry about one parameter which will affect the inter-antenna interaction, which actually has a very adverse effect on the MIMO performance, wireless communication performance, on data rate and diversity gain. That is the mutual coupling. Okay, so how do you measure this mutual coupling in the lab? So that's a discussion we are going to have. How do you measure this uh, mutual coupling in the lab. The device we use for measuring antenna performance is a network analyzer. So at the micro frequency, high frequency, you cannot measure current, you cannot measure voltage. The only measurable parameter is the scattering parameter. So the device which measure the scattering parameter is called the network analyzer, which will actually measure the antenna performance. So this is one typical network analyzer we use in our lab. It's made by Rhodes and Schwartz, ZDA24. This means this can work up to 24 gears. You can measure antenna performance from 10 megahertz to 24 megahertz. Look at this here. There are two ports here. This is a point for connection for network analyzer. You have port 1 and port 2. So using this port 1 and port 2 of the network analyzer, how do I measure the mutual coupling of the antenna, especially MIMO antenna? So let us consider this MIMO antenna, 2-port 2-element MIMO antenna. It also has port 1 and port 2. What do you do in the lab? You actually connect all the devices at the high frequency, micro frequency using coaxial cables. These are coaxial cables. These are used as a wire at the high frequency and micro frequency. What you do is you connect port 1 of this antenna with the port 1 of network analyzer with the port 1 of the antenna, and port 2 of the antenna with the port 2 of the network analyzer. Then you send some signals from port 1. How much signal is received by this port 2? That is your mutual coupling between port 1 and port 2 of the antenna. Okay, so 2-port 2-element MIMO antenna measuring the mutual coupling is very easy. But if you go for something called antenna with more number of ports, for example, okay, this is the anechoic chamber where we actually do the antenna measurements. So all these wedges here actually will absorb all the waves which are incoming towards these wedges, so that none of the wave will be reflected back and go to the antenna. Reflected waves are actually a hindrance in the antenna measurement. So these wedges will absorb the waves. We call this as quiet chamber or anechoic chamber. This is the one we have here in IIT Guwahati. So we want to measure the mutual coupling for this antenna here, this MIMO antenna here, and it has 6 ports. Port 1, 2, 3, 4, 5, 6. It also has 6 elements. But remember, our network analyzer was having only 2 ports. How do I measure the mutual coupling for such situation? So how do I do? Network analyzer has only 2 ports. This antenna has 6 ports. I want to measure mutual coupling port 1 and port 6. Then what do? I connect port 1 with the port 1 of the network analyzer, port 6 with the port 2 of the network analyzer. Then I send some signals and measure the signals which are coming to port 6. But then when I do this, what happens to these remaining ports? If I keep it open like this, there will be a lot of reflection, because you know that open circuit means infinite impedance. There will be a lot of reflection. So you have to put a match slot here, 50 ohm load here, so that there is no reflection. So with this setup, you can measure the mutual coupling within port 1 and 6. Like that, you can do the remaining thing for the other remaining ports. That's how you measure the mutual coupling in the lab. So let us look at some of the antennas we have designed in our lab. This is a 2-port 2-element MIMO antenna, and it works for 2 frequency. That's why dual band, dual port MIMO antenna. So now this antenna has 2 radiators, and see, look at this. This antenna and this antenna are connected with some printed lines here in this typical shape you have here. So this is basically one of the mutual coupling reduction techniques in antenna design. So if you want to reduce the mutual coupling between this antenna and this antenna element, you have to put some line which are called neutralization line. This will reduce the mutual coupling between antenna 1 and 2. So this is one technique people, antenna engineers, use to reduce the mutual coupling in MIMO antennas. Another case, you have 6-port antenna here. All these antennas are connected with this neutralization line here. This neutralization line will actually reduce the mutual coupling. Because of this neutralization line, there will be opposing current flowing here, which will actually minimize the mutual coupling. And this is another antenna. This is a DRA. DRA means dielectric resonator antenna, dielectric cylindrical dielectric resonator. So now this antenna and this antenna are very closely spaced. There will be a lot of interaction between this antenna. These antennas are excited by this cylindrical DRAs are accepted by these field lines here, and you have a partial ground plane here. So one important observation here is that we have something called grid lines here. We call this meta grid lines. So these meta grid lines are single negative metamaterials which will actually block EM wave propagation. Because of that, you'll have a very good mutual coupling reduction between these two antennas. Okay, another case study. This will be the last case study for the MIMO antenna design. We have 4 dielectric blocks here. These are dielectric blocks, and these are antenna which are radiating efficiently, but they are very closely placed. So there will be a lot of interaction between field radiated by this antenna and so on. So here we actually put a vertical metallic plate so that all the fields which has gone from here will be reflected so that it won't be able to reach to the other antenna. So no need to worry about that. So fields produced by this kind of dielectric resonator antenna can be classified as transverse electric. Transverse means it's an English word, it's perpendicular electric. If your fields are propagating in y direction, transverse electric means fields will be confined in xy plane. TEX means fields are propagating along the x direction, then your field will be confined in the YZ plane. That's what this diagram will show. For TEY, field is propagating along the y direction, but your field will be confined in XZ plane. Similarly, for TEX, your field is propagating along the y direction, but the field will confine in ZY plane. Let us look at the field pattern. So the field pattern for the dielectric block 1 and dielectric block 3 is similar because of the fit we have given was very similar, and it will excite this kind of TE modes we have told, TEY 1 delta 1 mode. You can observe that TEY mode, where is the y-axis? Y-axis is along this direction. So you don't have any fields are confined in the XZ plane. Similarly, if you have observed the fields for dielectric block 2 and dielectric block 4, the field patterns are very similar because the field fit we have given was along the same direction. Excitation we have given to the antenna was very similar for dielectric block 2 and dielectric block 4. So the field pattern will be very similar. We have TX delta 1 mode. TEX means field will be confined in XY plane. This is X direction. We don't have any field along this direction. We have field confinement in the YZ plane. Okay, so what is the effect of the vertical metallic plates we have used? Let us try to see that. These are the field radiated from the 3D radiation pattern of all the antennas, 4 antennas we have considered here. What you see here is that this antenna and this antenna has similar kind of radiation pattern. This antenna has similar kind of radiation pattern because of the fit and the excitation we have given was very similar. So this field and this field, there will be a lot of interaction here. This field and this field also, there will be a lot of interaction. But after we put the vertical metallic plates, what you see here is field here and field here has become yellowish. Red color means there's a lot of radiation, radiated fields. Yellowish means field has been reduced. Again, here also you can see that field has been reduced here because of the vertical metallic plates. That's how it actually minimizes the inter-antenna interaction or mutual coupling between the antenna array. So we compare our antenna performance with the existing work in the literature. What you can see is that our antenna is having either better or comparable bandwidth with the antennas which has been reported in the literature. And another thing is that port we have used is 4. Most of the antenna has used 4 ports or 4 elements. Size of the antenna, look at the size and mutual coupling. Our mutual coupling is very good. Below the minus 15 dB is around minus 20 dB, which is very good. So this MIMO antenna will have very good performance because mutual coupling is less than minus 15 dB, even better than the existing antennas. You look at the size of our antenna is smallest one. So we want to minimize, make more and more compact MIMO antenna array, and our antenna is a very compact antenna and it's a very good performance. This is one of our work which has been recently presented in International Symposium on Antennas and Propagation in Osaka, Japan in January 2021. Okay, let us do some kind of metric calculation here. So question is how many antennas we can fit on a mobile phones. So look at the mobile phone. Typical length of mobile phone is around 15 centimeter. And how many antennas we can fit on such kind of smartphones. So let us try to understand. You have antenna 1, antenna 2. The distance between antenna 1 and antenna 2 is called inter-element spacing, IES, inter-element spacing. Traditionally, all antenna array has inter-element spacing of lambda by 2. Lambda is the wavelength, lambda by 2. So if you consider GSM mobile phones which work at 1 GHz, how much is lambda by 2? Lambda by 2 is 15 centimeters. So antenna will also have some finite dimension and distance between them is 15 centimeter. You cannot fit in more than one antenna on GSM mobile phones. Okay, now let us go to the 5G wireless communication. 5G wireless communication has two frequency regions. One is sub 6 GHz. It's called 5G NR1. 5G NR-FR1, 5G new radio frequency range 1. So this is sub 6 GHz range. Any frequency below the 6 GHz should be able to work for 5G NR-FR1. So let's say around 3 GHz. How much is lambda by 2 or wavelength by 2 is around 5 centimeter. So now our mobile phone dimension was 15 centimeter. If lambda by 2 is 5 centimeter, we can easily fit in 2 antennas on a 5G mobile phone. For example, you go to 5G NR-FR2, 5G new radio frequency range 2, which is projected in millimeter wave 24 to 100 GHz. See, at 30 GHz, how much is the lambda by 2? Lambda is the wavelength. Lambda by 2 is half centimeter. So now if you go for 5G NR-FR2, then you can easily fit in 15 mobile phones, 15 antennas on a single mobile phone. So that's why one of the reasons people are going for higher and higher frequency of operation for the wireless communication. If you go to higher and higher frequency millimeter wave terahertz, your device size is going to become smaller and smaller and compact. So if you go work at 5G NR-FR2 on a mobile phone of lateral dimension 15 centimeter, you can fit in 15 antennas. So the performance is going to improve drastically. See, 15 antennas and one antenna performance, even the data rate will be improved 15 times. So if you go for higher and higher frequency, you'll have higher and higher data transfer rate because of this form factor you have here. Okay, so that's about the inter-antenna interaction in MIMO wireless. Let us try to look at the evolution of the MIMO wireless over time. So this is the multi-user MIMO. First MIMO was single-user MIMO. You have K users here served by one base station with 10 antennas. And every mobile user is using 2 antennas. We have K mobile users here. So as I've told you, we'll have uplink because this base station is at higher elevation. Signal you send from the lower elevation mobile phone is called uplink. And you have downlink communication here when your base station is sending signal to the mobile users. Okay, so for the multi-user MIMO system, we have considered here is our antenna here. Our antenna we have designed. If you assume that these mobile users are employing our antenna, and we have 3 of them, 3 users here, it's a case study, then how much is the channel capacity reduction? How much is the reduction in the capacity due to the inter-antenna interaction? We have calculated it for multi-user MIMO system. It turns out to be 0.0001 bits per second per hertz. So when I employ this MIMO antenna, our MIMO antenna, which has been designed for the mobile phones, and in the multi-user scenario, if I find out the channel capacity loss, how much is the reduction in the channel capacity due to the antenna interaction? It is very small, 0.0001. But if you consider this for a single user MIMO, where only one user is there, in that case, the capacity reduction is much, much higher, 0.0925 bits per second per hertz. So the speed reduction in the single user MIMO is much higher than that of the multi-user MIMO. That's also one of the reasons why people has gone from single user MIMO to multi-user MIMO. So let us do case study. Second case study. This is one of the recent antenna published in April 2021 in IEEE Transaction on Antennas and Propagation. This antenna, MIMO antenna, has 4 elements, 1, 2, 3, 4. And if you assume that such kind of antennas you use in 5G terminal and find out how much is the channel capacity loss due to inter-antenna interaction, it is very small, 0.0014 bits per second per hertz. That's a reduction in the speed due to antenna correlation or antenna interaction in this 4-element MIMO antenna array. Similarly, if you look at one of the recent paper published in IEEE Transaction on Antennas and Propagation, if you see, the good thing about this antenna is that this antenna has 8 elements. So on a mobile phone, they have fitted 5G mobile phone, they have fitted 8-element antenna array. And we want to see how much is the channel capacity loss due to this 8-element MIMO antenna on a 5G smartphone in a multi-user scenario. So the channel capacity loss is 0.0050139, which is very less. So this kind of antennas are very efficient antenna design. And you may be surprised, in 5G smartphone, we can fit in 8 antennas and it's performing very good. Okay, so that was about the multi-user MIMO. Multi-user MIMO actually evolved to massive MIMO. Massive MIMO, multi-user MIMO is used in the 4G wireless communication, mobile communication, and massive MIMO is used in the 5G wireless communication. In the massive MIMO, what is the principle behind this massive MIMO is that, for example, you have this base station antenna, M antenna is communicating with another terminal with K antennas. So now, this is a point-to-point or single-user MIMO communication. But let's say you consider another situation where this antenna, you look at the inter-element spacing here is very less. Antenna 1, 2, the inter-element spacing is very less. But look at the mobile users here. These mobile users are very far away. One mobile user is very far away from another antenna of the another mobile user. So, but this antenna, no, inter-element spacing is very small, in the order of, millimeter or very small. Huh? But mobile user to another mobile user is always in the order of meter. Huh? Distance is very far away. So the idea is, why don't we distribute this antenna of the mobile terminal here to every mobile user? So inter-element spacing between the antennas will increase. Because of this increase in the inter-element spacing between the antenna, the diversity gain is going to improve. Rate gain is going to improve. So inter-antenna interaction is dependent on the inter-element spacing, but mobile to mobile user inter-element spacing is much larger than antenna to antenna element spacing. So we'll have a better diversity gain and rate gain. So that was the idea of this multi-user MIMO and massive MIMO. In the massive MIMO, usually base station will employ hundreds or more of antenna. In the traditional multi-user MIMO, which was used in 4G wireless communication, base station employs around 10 antennas. But in the massive MIMO, it's already employed more than 100 antennas in the base station. And because of that, it will have very good performance. And even the processing you do at the base station has been simplified significantly when the number of antenna is tending to infinity. Okay, so let us discuss about one very difficult problem cellular structure has from the beginning. So you have a base station with base station antennas here. This is a cell which is served by this base station 1, cell 1. You consider a user here at the boundary of this cell 1. So now this mobile phone is very far away from this base station antenna, but this mobile phone is very near to the base station antennas of the neighboring cells. So all the neighboring cells base station antennas are very near to this mobile user at the edge of the cell 1. From the home base station, this mobile user is very far away. But from the neighboring cells, it is very near, so it start picking up signals from the neighboring cells. And this is actually called interference. Desired signal is coming from the base station, home base station. Interfering signals are coming from the neighboring cells. So there is something called signal to interference noise ratio. This is the desired signal divided by the noise along with the interfering signals. So SINR, signal to interference noise ratio. So higher is the signal to interference noise ratio, the capacity data transfer rate is going to increase. But if this decreases, then capacity of data transfer rate is going to decrease. SINR is calculated as power desired divided by the power interfering. So here, this mobile user at the cell S is getting very less signal from the base station, home base station. This is a desired signal. The desired signal is very small, but interfering signals from the neighboring cell is very high. So this ratio is going to be very, very small, and the data transfer rate capacity is going to be very small for the cell user at the edge. So this is the inherent problem in the cellular communication from the beginning. So it is unsolvable. So this is called near-far effect, near to the interfering cells and very far out from the home cells. So near-far problem is an unsolvable problem in the cellular communication from the beginning. So there is a cure for that. People are proposing something called cell-free massive MIMO. In the cell-free massive MIMO, the concept of cell is completely eradicated. There is no cell. So every user is surrounded by many access points. So user will be getting the best performance from nearby access points. So there is nothing like cells. The whole geographical area is surrounded by many access points which are connected to the CPU, which will do all the processing. And at any particular point of time, user is always surrounded by many access points, so it will get the best performance from all the surrounding access point. There is no location where user is not surrounded by access points. So you will have many access points which is distributed over the geographical area, which are connected to the CPU, central processing unit. So now this is the best situation for the user. User will not have any kind of, see, basically your all cellular communication system were network centric. So whenever you have network, you'll have very good communication. Whenever you don't have network, there won't be any very good communication. But here, this is called user-centric approach. User has been given the first preference. What is the best situation for the user? Best situation for the user is when it is surrounded by many access points. So geographically, all these access points will be distributed over the geographical areas, and user will be always connected with some of the access point, which will give best performance for the user. So the idea here is that, as I have told you, in the base station, this inter-element spacing between the antenna is very less. Because of that, diversity gain and rate gain is not going to be good because of more antenna interaction. Antenna of the base station to all the access point here, then inter-element spacing is very large here. So we'll have a very good rate and diversity gain. So that was the idea of cell-free massive MIMO. And another idea is that we don't have any cells here. So this has very good performance. We'll see from the next two slides. So here, the performance is actually affected by the something called spatial correlation. So this is the base station antenna. Base station is at higher height. So usually base station doesn't have any kind of scattering because number of scatterer for the base station at higher elevation is less. But mobile user at a lower elevation, it will be always surrounded by scatterers. So if you assume that this mobile user is sending signal to the base station and all the signals which has gone through reflection, refraction, all the multipaths from this user is confined in one area, this area here, and we define this angle as center angle as nominal angle and this angle as standard deviation, angular standard deviation. We can come up with one local scattering model, and using that model, we can actually find out the capacity for the MIMO system. And with this local scattering, which is called correlated case, another is called uncorrelated without local scattering. So in the practical scenario, there will be always correlation. So what you can see here is that uncorrelated case, this is the capacity versus transmit power. So you can see that all these red curves here without any correlation is having the best performance. Capacity is higher here. When you have correlation, then capacity has been reduced. And this curve is for the massive MIMO, and this curve is for the cell-free massive MIMO for the uplink case. And what you can observe is that cell-free massive MIMO has higher some rate or capacity than the massive MIMO. Similarly, this is for the downlink case, this is for the massive MIMO, and this is for the cell-free massive MIMO. So from this graphs here, you can observe that cell-free massive MIMO has much better performance, higher data transfer rate than the massive MIMO. And because of the correlation, the data transfer rate has been reduced. Okay, so let us come back to the one of the technique for future, which is radio stripes network, which are actually invented by Paul Franger and Jan Hederen from the Ericsson, Sweden. They actually invented this technology, which is radio stripe networks, and they have not disclosed how they are going to make the circuits for the cell-free massive MIMO using these radio stripes. All they have shown is the cell-free massive MIMO will have circuits which are actually printed on a very thin layer material like shallow tape, and it can be rolled out tape on any kind of structures. So this is radio stripe networks where all the circuits are printed on this very thin sellotape like structure, and you can stick it on wall, on building, on a train station, and this will actually be rolled out for the 6G wireless communication for cell-free massive MIMO. This is a key enabler for the cell-free massive MIMO, which is proposed for the 6G wireless communications. So the idea is, in future, there will be a lot of traffic. Many mobile users will be using mobile phones for many high definition applications, high definition video or applications. So for example, this is one scenario where you have many users actually going on a public transport, and most of them are doing something on their mobile phones. It could be watching movie, or they are doing video conferencing, those kind of situation. So there will be a lot of mobile traffic here. So the future network, which will actually support this kind of heavy traffic, is by using radio stripe network. So you can see here this red color structure here. You have a radio stripe network which are actually rolled out in the ground floor, on the door, on the side walls, windows. So this kind of radio stripe networks will give the ubiquitous communication almost anywhere, everywhere. Next is in the train station. Also, many users are standing here and they are doing something with their mobile phones. So every user will have very heavy traffic here because there's a lot of users here. So in order to give very good quality of service and data transfer it to all the users who are in the train station, you need to have a radio stripe network here. These are radio stripe networks on the walls, on the rails, so you can put it anywhere. Similarly, the example I have given at the beginning, on a city square, many users are using mobile phones, so there will be heavy traffic. So we can put cell-free massive MIMO in the future wireless communication. So the first paper on the radio stripe networks after the invention of radio stripe networks by Paul Franger is this first paper here. There they have actually mentioned about the radio stripe networks. And this paper is the second paper on radio stripe networks, and they have actually suggested how to implement this kind of radio stripe networks. And radio stripe networks are actually used for connecting access point with the CPU. This will actually replace all the coaxial cables in the future for connecting access point using to the CPU. And on the radio stripe networks, you will have antennas, also all other processing units. That is the projection they've made. Okay, so there's one science or technology which is called surface plasmon polarity. This is basically, these are electromagnetic waves that travel along a metal dielectric or metal air interface. So this surface plasmon polaritron was existing at the optical frequency, and can we have this suppressed plasmon polyton wave propagation at the metal directly or metal layer interface at the micro frequency? And this has been actually proposed by famous Sir John Pendry. Sir John Pendry is very well-known person in the micro community for his invention of many things like metamaterial structure or smooth surface plasmon polyton. So here in the paper in the Science, mimicking surface plasmon with structure surface, he has actually proposed that this surface plasmon polyton can also exist in micro frequency, and you can observe that this single paper in the Science by Sir John Prendy from Imperial College London is having 2,857 citations. So this kind of paper has very high impact. So you can understand that obviously this kind of paper has a lot of impact in the research in the suppressed plasmon polyton. So he made original proposal of suppressed plasmon polyton, which is actually mimicking the suppressed plasmon polyton at the optical frequency at micro frequency. So using this concept, Professor Sway and his group, Professor Sway is a very well-known person in the field of metamaterials. He has actually proposed a conformant suppressed plasmon polyton. So you can see here, this is a thin layer here. Here you have put some kind of printing here. You can fold it, you can roll it. And because of this gratings here, you can actually excite, surface plasmon polyton structure at the metal air interface, metal air dielectric interface. And the one good thing about this is conformal. It can be fit into any kind of structure. It can be rolled out. It can be folded. So we actually thought that this is a very good idea for implementing radio stripe networks. And we actually implemented a conformal suppressed plasmon polyton structure. We actually designed a filter. This is the structure of the filter. And we actually thought that this kind of structure could be a possibility for radio stripe networks. And this filter has a very good filtering performance. You can observe that it is having a bandwidth from 0 to 12 gigahertz. This is a low pass filter. And we actually project that this kind of filters using conformal surface plasmon polyton structure could be used for radio stripe network. This is an unpublished work we have recently submitted. Okay, these are the references. And thanks a lot for your patience. And if you have any questions, I can handle those questions. Thank you very much.